So the lecture notes, lecture notes and the slides should now be in Sakai, so you should be able to follow along just fine.
Oh, Professor Goins, actually, I have a question. Like,
Sure.
on Sakai, it seems that the lecture note, which says lecture 23, is actually lecture 22, and the one lecture 22, 21 seems to be actually lecture 20, no, 30. Yeah, sorry, I was saying something now. 33, actually 32 and 31 actually.
33. Okay, I'll take a look at them. I'll see what the deal is. Hopefully things are not out of order. It may just be that I got something screwed up, but yeah, thanks for letting me know. So I'll take a look at 31, 32, and 33 just in case. Right. So let's just start with a few announcements and a quick recap of things. Wednesday's lecture should now be on YouTube, so you should be able to follow along pretty well there. Office hours are at the usual time, usual place, so I'll be around from 11 to 12 Pacific and then from 4 to 5 Pacific. I'm sorry, the last few days I've actually not been around from 4 to 5 because some things have come up and I haven't really felt well, but I should be around today for the whole time. And as a quick reminder, homework set number 8 is due today, and homework set number 9 will be due next week. As I was saying earlier, if you feel a little bit too stressed and that you don't have time to turn in these homework sets, that is perfectly fine. The goal of these sets is just to help expand upon what we're doing in lecture. So to kind of maybe walk you through some of the proofs of some of the things that I'm saying. So that'll be, for example, what we'll do for homework set number 9. It'll expand upon some things I'll say today. I plan to have number 9 posted this weekend, so it'll be up in a couple of days. Okay, so let's do a quick recap of where we were Wednesday. Remember that we're assuming F is an algebraically closed field, so think of F maybe as the complex numbers, and let's let R be this polynomial ring in n variables. So last time we were getting into this concept of quasi-affine varieties, and we started with the idea of affine N-Space. So simply put, it's just going to be the collection of n tuples here. So just elements A1 through AN, we put together into something we'll denote as P. And remember that we have an embedding that allows us to take an n tuple, P, and associate that with a maximal ideal, MP. And of course, we know that because we're working over an algebraically closed field, that every such maximal ideal arises in this form. So we're going to abuse notation, and we'll denote AN of F as spec of R, as all of the prime ideals. Of course, this is abusing notation because actually this really should be M spec, but we'll just throw in the ideal that corresponds to the 0 ideal and just not really worry about it too much. Now, an affine variety is a subset which we'll denote as X, which is, just using the parlance, irreducible, non-empty, and Zariski closed. So of course we have to make sense of what all of that means. So first of all, saying that it's irreducible means that we form this set IX. This is an ideal, and actually we're assuming that it is a prime ideal. So that's what it means to be irreducible. And once we do this, then we can look at this quotient ring, O, which is R mod this ideal, and this is the coordinate ring of X. So the whole point here is that irreducible means that the coordinate ring is an integral domain. Next, when we say Zariski closed, what that means is we can take a look at the 0 set of this ideal. So that is just the set of points that vanish for everything in the ideal. And we're assuming that this Zariski closure is equal to X itself. So that's what it means to be Zariski closed. Right, so any affine variety that again is irreducible, non-empty, and Zariski closed is what we'll call an affine variety. Now, just like before, we could talk about affine N-Space looking like spec R. We'll write our affine variety as spec O, where O here was the coordinate ring. And actually, one of the really amazing things about algebraic geometry is that you can work in the opposite direction. So that is, given an integral domain O, we will define an affine variety in this way, just spec of O. Right, so we're going to try to play around with these ideas a bit more over the next couple of lessons. So remember that we spend some time discussing what does it mean to be a non-singular variety. And we'll say that our x here will be non-singular precisely when our coordinate ring, O, is an integral domain which is both Noetherian and integrally closed. Right, so this will be our definition of what it means to be a non-singular affine variety. And remember that we proved before that if x looks like it's being defined by m polynomials and n variables, then non-singular just means that the tangent space exists at every point. Okay, that's kind of the philosophy. Right. Finally, we'll define the dimension of our affine variety as the Krull dimension of its coordinate ring. Right, so this will just be our simple definition. If we're given an affine variety, we talk about what does it mean to be non-singular, and then we can talk about what does it mean to have a dimension.
I have a question.
Sure.
So I kind of remember that previously we defined like a variety is singular, is non-singular in terms of the cotangent, the dimension of the cotangent space. So how is that definition related to the definition here?
So this is a fancy theorem in commutative algebra. And the theorem says that if your cotangent spaces have dimension n minus m, where n is the number of variables and m is the number of polynomials, and if this is true for every maximal ideal, then your coordinate ring is integrally closed.
Okay.
Yeah, so that is a theorem from commutative algebra, and there you'd have to read about that in this book that I mentioned by T.M. McDonald. But so instead of us trying to get into what does that fancy theorem mean, here I'm just kind of cutting corners and just saying a non-singular variety just means it's Noetherian and integrally closed.
Thank you.
Yeah, you're welcome. All right. Now we can define a quasi-affine variety. So simply put, it is a non-empty subset U, which is Zariski open for some affine variety X. Okay, so that's what we mean by quasi-affine. It's just some Zariski open subset of an affine variety. So another way to say this is that we want our U to look like the variety minus the zero set of a certain subset T that satisfies this. So of course, T is a subset of our polynomial ring R, but T should also contain this prime ideal IX. This is just a guarantee that Z of T is a subset of X. But that's all that we're defining this here. So again, the prime ideal is contained inside of T, just forces Z of T to be a subset of X, so that this difference here makes sense. Now, as before, we were trying to write everything in terms of spec of our coordinate ring. We can do exactly the same thing here. So we'll abuse notation and say that a quasi-affine variety will look like this, a subset of spec of O, where now we do not want to include those prime ideals I that contain this coset T bar. That's all that we want to do. We want to make sure that we're going to keep those prime ideals that do not contain this coset, right? And of course, that's what it means to be open, that it just doesn't contain a certain set here. So just like before, we can talk about what does it mean to be non-singular. So we'll say that our quasi-affine variety is non-singular if we look at the Zariski closure, which we'll call U bar, and if that is a non-singular variety. So now we just translate everything back to a Zariski closure, and the point is that the Zariski closure is an affine variety, so this makes sense. And finally, we'll define the dimension, just like what you would expect. It's just the dimension of the Zariski closure, right? Because again, the Zariski closure is already an affine variety, so we know how to define it. Right? So then we talked about the specific case of the affine line. So this was n is equal to 1, or if you will, A1 of F. Right? So just all of the numbers in F. And we talked about there, what does it mean to be an affine variety, and what does it mean to be a quasi-affine variety? So we found that every affine variety X only comes in one of two types. Either it's the whole affine line, or it's just one point. So remember that we said that every Zariski closed set of the affine line, this was a homework assignment, was either the whole line or a finite set of points. But here, because we're dealing with an irreducible variety, then we can either have the whole line or just one point, right? But we can only have these two types of possibilities if we're dealing with an affine variety sitting inside of the affine line. Similarly, every quasi-affine variety, which we'll call U, is either just one point, or it's the affine line minus a finite number of points. So again, those are the only two possibilities if we're dealing with a quasi-affine variety. I want to point out that in these two cases, we actually know what the Zariski closure is. So if we just have one point, that's already Zariski closed. So Zariski closure is just the set consisting of one point again. However, if we're dealing with the affine line minus a finite number of points, so again, this was a homework assignment, then the Zariski closure is just the whole affine line again. Right, so again, these are now the only possibilities of the quasi-affine variety and what its Zariski closure would be. Okay, so already for the affine line, we actually know a lot. We know what affine varieties look like. We know what quasi-affine varieties look like. Okay, so today what I want to do is discuss what do we mean by a projective variety, and then what do we mean by a quasi-projective variety. So I'm going to introduce a lot of definitions today because this is kind of a weird technical aspect in algebraic geometry. And then I want to come back and then do a lot of examples on Monday. So just think today is kind of the weird day where we're just going to go over lots of examples. And then Monday we'll come back and then try our best to make more sense of these definitions. So let's start with what we know. Let's talk about projective N-Space. So by projective N-Space, what we just mean is a collection of equivalence classes, which we'll write this way using the colons, where here we'll take 2 points. In fact, we'll take two n+1 tuples. Let's write it this way as P and Q. And we'll say that they're equivalent if I can find a number lambda where each AK equals lambda times BK. Okay, so again, we already know these are just equivalence classes where we take these n+1 tuples and we just say that they're equivalent if they're scalar multiples of each other. From there, we then define homogeneous polynomials. So let's let S be the polynomial ring here in n+1 variables. Right, so we'll start at x0 as opposed to x1. And we'll say that a polynomial is homogeneous of degree E if whenever P is lambda times Q, then f of P is lambda to the E times f of Q. Right, so again, we're just going to kind of factor out this power of lambda. And from here, we have this very fancy theorem. So let me try to walk you through what's here, and then we'll kind of come back and then maybe work through some examples here. Again, let's let S be this polynomial ring in n+1 variables. And let's denote SE as the collection of homogeneous polynomials of degree E. Right, so take all of these homogeneous polynomials, put them together into one subset, call this SE. So there's 5 statements that I want to go over here. First, when E is equal to 0, homogeneous polynomials of degree 0 are just constants. So what we're calling S0 is just our field F. Right, so again, every constant polynomial just looks like it's just a number from F. Right, next, in general, this SE is a 2-sided F module. So what that means is, if I take F and G, homogeneous polynomials of degree E, then the sum is a homogeneous polynomial of degree E. And if I take any element from F, call it A, then this product is a homogeneous polynomial of degree E. Right, so that's what I mean by an SO module. So I just say that I can add things together in the set and get back things in the set, or I can multiply something in the field times something in the set and get back something in the set. So that's what we mean by a module. Now you may wonder, well, why don't I just try to multiply things together in the set? Well, here's where I have to be a little bit careful. Say that I have a homogeneous polynomial of degree I and another one of degree j. So if you stare at the definition of being homogeneous of degree I, of course here I need like a lambda to the I, and the point is that the product is actually a homogeneous polynomial of degree I plus j. So the exponents actually add, and that's the statement here. Right, so again, if I take a homogeneous polynomial of degree I and another one of degree j, then the product of those two is a homogeneous polynomial of degree I plus j. Right. Fourth statement is the intersection of any of these two sets is the zero ideal. Right. So what I mean by that is, if I and j are different from each other, then Si intersect Sj is zero. So here's how to think about this. Give me a homogeneous polynomial that has degree 2 and it has degree 3. Well, if you think about it, there is none that's going to have both degree 2 and degree 3 unless it's the zero polynomial. So that's what this says here, right? That if I have a polynomial of degree I and of degree j, then the only way that they can simultaneously happen is if we're dealing with the zero polynomial. Okay. And finally, this says that every polynomial can be expressed uniquely as a sum of homogeneous polynomials. So we're going to write that using this fancy notation here. So when I write this circle plus, this actually means what's here in parts 3 and 4. So the plus means that I can think of everything in S as being in at least one of these SEs, right? In at least one. So I can write every polynomial as a sum of homogeneous polynomials. But the circle around the plus means that there is exactly one SE where they lie, if I do the sum. But that's exactly what was here in part 4, right? That the intersection here is the zero ideal. So again, the circle plus really means two things. It means number one, I can write every polynomial as a sum of homogeneous polynomials. And number two, the circle around the plus means that the intersection, as long as I is different from j, is the zero ideal. Right, so that circle plus actually means quite a bit when you put it all together. Yes.
Actually, I have a question.
Sure.
So why is 0 contained in Si?
Well, 0 is a homogeneous polynomial of degree E for any E.
Oh.
I mean, just stare at the definition here. What if both sides are equal to 0?
Thank you.
Right, yeah, then that has to hold for any E. It doesn't matter at all what E is. So yeah, thanks for that. So because we have these 5 properties here, we call this S a graded ring. Right, so again, a graded ring simply put means that it satisfies these 5 properties. So the constant polynomials really form this field. We know that each SE is an SO module. The product of these look like SI times SJ is contained in SI plus J. The intersection of SI and SJ is the zero ideal. And then you have here this so-called direct sum of the various parts. Okay. All right, so let's talk about some examples here, because this is a fancy theorem. There's a lot of weird stuff going on here. So I'm going to try to break it down to say what's happening. It's actually not as bad as it looks. So I'm going to take a closer look here at this graded ring, at this polynomial ring in n plus 1 variables. So SE remember, is the collection of homogeneous polynomials of degree E. So what is S0? So here I need to ask, what are my polynomials that have degree 0? Well, the only ones that have degree 0 have to be the constant polynomials. Right, so that's what I mean by A an element of F. It's just a constant polynomial. Just takes on the value A no matter where we are. So what about S1? S1 should be all polynomials of degree 1. Well, if I take a look at xk, those are my n plus 1 variables. So my polynomials of degree 1 look like this here, where my coefficients lie in F. Right, so there are n plus 1 of these coefficients sitting here. But again, this is what the set of all linear polynomials looks like. So again, homogeneous of degree 1. Homogeneous of degree 2 just means I need to make sure that I have the product of two things here. And again, the coefficients aij lie in F. So this would be what all of my homogeneous polynomials of degree 2 would look like. So just the product of xi's, xj's. Right? Okay. So now if I kind of stare at these three examples just to get some ideas of what's happening, then I see, for example, that S0 here is F, right? That's exactly what the theorem said. Now, if I take the product of something of degree 1 times something of degree 2, then you'll see here, if I take the product, I'll have something that looks like xi, xj, xk. So now I'll have 3 of them, and that's why the product here lies inside of S3. Right. Finally, what if I take a look at the intersection? So now I want to ask the question, when is this polynomial here of degree 1 the same as this polynomial here of degree 2? Well, the weird thing is, here I see that xk only appears once, and here, xi, xj, I have kind of 2 of those. So there's no way that these two could be equal to each other unless all of the coefficients here were 0. Right? But that's exactly the statement here. Right? The only way that I can have a polynomial of degree 1 and it has degree 2 is if all of the coefficients are equal to 0. Right? I just can't set these equal to each other because I have too many variables. Or well, I should say I have the wrong degrees with the variables. Okay, any questions on this example here? What we said with the graded ring? Okay, let's try to move on here. Now, with the affine N-Space, we had this idea of Zariski topology. So now that we're going to generalize a little bit to projective space, I want to be careful to say, what should the Zariski topology look like in this case? So much in the same way we defined a topology on the affine N-Space, we're going to define a topology now on projective N-Space. I'm not really going to worry about proving things, that I'll leave for the homework assignment, but I just want to say a few things here. So first of all, we'll say that a subset is Zariski closed if it's in this form here for some t. I mean, hopefully this kind of makes sense. I mean, here I just kind of replaced what happened with affine space now to projective space. So it's just the set of projective points that is the 0 locus for some subset t. Here's the difference. I want my t to be in a very specific form. Right, so I'm going to come back a little bit later and say why we're doing this. Because I know when you first look at this, it doesn't make any sense why we're saying this here. So what this says is the following. Remember that our set S, this was our polynomial ring, that was a graded ring. I want to keep the same grading on this set T. Intuitively, what we're trying to say is this. I don't just want to pick any polynomials in S. I want to be careful to pick the ones that are homogeneous. The reason being, remember that my point, excuse me, my point P here I really only have it defined up to scalar multiple. Because remember that here I have equivalence classes. So I can only make sense of this here if I'm dealing with a homogeneous polynomial. And that's what this here says, that my set T really consists of homogeneous polynomials. Right? That's the weird condition here. So again, this here forces T to consist of only homogeneous polynomials. In a similar way, we can define what does it mean to be Zariski open. So we'll say that a subset is Zariski open if it's the complement of a Zariski closed set. Right? So hopefully that's not very surprising. And then you just kind of run through exactly the same argument as what we did with affine N-Space, and then you just prove that now we have a topology. Right? So things such as the union of two open sets is open, and the intersection of two open sets is open. You know, things to this effect. Right? But again, we'll work out more details for that. Okay. Any questions here on how we worked out the Zariski topology for projective N-Space? Okay, the main thing to remember here is that we're not allowing just any subset, but one a subset that corresponds to homogeneous polynomials. Okay, that's the subtlety here. Okay, now we get into the big definition that we wanted to do for the day. So what is a projective variety? What's the general definition? So projective variety, just like what you would expect, is a subset of projective space that is irreducible and Zariski closed. The caveat here is that it's in the Zariski topology on projective space, but it's still the same wording, an irreducible, non-empty Zariski closed set. So let's try to make sense of what that means. So first of all, irreducible means that we better have a prime ideal. So let's form the set just like you would expect. And now we just want this here to be the set of polynomials that vanish along all of x. Again, just like what you expect. And this here better be a prime ideal of S. Here's the difference. Now, I need to have this weird condition here on this ideal. So again, remember that we want to keep track of the grading, because somehow what we're trying to say is that we want homogeneous polynomials. So the intuition here is that Ix should consist of polynomials, but I want those polynomials to be homogeneous. That's what this condition here says. Okay, so that's what it means to be irreducible. And now we can just say that we want it to be Zariski closed. And again, it's exactly what you expect. I just want to make sure that X is equal to its Zariski closure. Right, so there isn't any difference here. So now we can define things like the coordinate ring and the dimension and all of this stuff. So our homogeneous coordinate ring here now is this quotient exactly in the way that you expect. So remember that our S is polynomials in n+1 variables. The Ix here, this is prime ideal. And now the only condition that we have to worry about is that this coordinate ring is actually a graded ring. Right, so again, we want to somehow keep track of the homogeneous polynomials because we are dealing with these equivalence classes in projective space. So again, we have a coordinate ring just like what was before, but now the condition here on this prime ideal says that our homogeneous coordinate ring is actually a graded ring. Right, we just get that for free. In general, we'll say that a prime ideal is a homogeneous prime if it's in this form here. Right, so it just satisfies this condition. So it's like it's a grading. It just says that it's generated by homogeneous polynomials. So simply put, we want to make sure that our prime ideal is an homogeneous prime ideal, and then that forces our coordinate ring to be a graded ring. Finally, we'll define the dimension of our variety in this weird way here. The dimension of a projective variety is 1 less than the cruel dimension of the homogeneous coordinate ring. So I don't really want to get into why this is true. This actually is a slightly nasty exercise that you have to do in a typical algebraic geometry course. If you wanted to see how this worked out, I would say look at this book by Robin Hartshorne named simply Algebraic Geometry. And it's within the first 10 pages or so of the book. But this is something I don't really want to go over in this course just because the proof isn't really something that is going to be worth it for us to work on. So for the moment, we can actually use this as the definition, as opposed to trying to say that this is equivalent to some other fancy definition using topological spaces. So again, the dimension of a projective variety is 1 less than the cruel dimension of the homogeneous coordinate ring. Okay, so finally, let's define a quasi-projective variety. And again, it's going to be exactly what you expect. Quasi-projective is a subset that is Zariski open in a projective variety X. It's not any more complicated than that. All you have to remember is that we're working with the Zariski topology. So let's be a little bit careful what this means. That is, we want to say that U is the complement of something in X. So the complement here should be this Zariski closed set, but actually this set corresponds to T satisfying a few properties. Number one, it better contain IX, right? That's just the guarantee that ZT is a subset of X. So this is not any different than what we did for the quasi-affine varieties. We want T here itself to be a homogeneous set. So again, we just want T to be generated by homogeneous polynomials. So hopefully that's not too surprising. And the third one is this one here. So this, remember, we have this condition here that the prime ideal IX is contained in T, but now if I keep track of the grading, then this says that the grading of the prime ideal X is contained in the grading of the prime ideal for T. So this here is also not very surprising. This more or less follows from the first one here, but I'm just stating the third one here just to really hit home that we really are trying to keep track of the gradings. So here you can think of this in the following way. SE consists of homogeneous polynomials of degree E. So that says that the homogeneous polynomials of degree E in T have to be contained over here. And this says that the homogeneous polynomials of degree E in the prime ideal are contained in those homogeneous polynomials in T. So again, this more or less follows from the first one, but I just want to emphasize that you really have something with the grading happening here. You just want to keep track of all of the homogeneous polynomials. And then finally, we can define the dimension just like the way you would expect. Let's first define the Zariski closure in this way here. And then the dimension is just going to be the dimension for the projective variety U bar. Right? The Zariski closure is a projective variety. So I can just define it in this way. Okay, so any questions on just kind of these big fancy definitions for now? Okay, remember that on Monday, we're going to come back and we're going to focus on some examples here. But I wanted to at least introduce everything today because it does take a while to kind of sink in what's happening. Now, what I want to do for the last 8 minutes or so of class is try to figure out how does this all relate to what we were saying before about spec of O. So is there kind of a fancy way we can do all of this by looking at things like prime ideals? So first, let's try to focus on projective space just to get an idea of how all this works. So let's say that X here is Pn, and remember that S is this polynomial ring in n variables. So I'm going to prove that this here is a projective variety. Okay. So first of all, let's take a look at our prime ideal, Ix. And remember that we're asking for what are all of the polynomials that vanish at everything in X. Well, because we have the entire space, the only polynomial that vanishes everywhere is zero polynomial. So in this case, if we're dealing with the whole projective N-space, this prime ideal is the zero ideal. Notice that this was exactly what happened when we were dealing with affine N-space. Same idea. So now let's ask, what about the homogeneous elements? Well, we see here that if we take a look and ask, what are the homogeneous elements of degree E? Well, it's just the zero ideal again. So even in our grading, the homogeneous polynomials of degree E are exactly the zero ideal. Sorry, I should say the zero polynomial. So now we get this here for free. The reason being, Ix over here on the left is zero, each one over here on the right is zero, so the direct sum is zero. It's like I'm adding 0 plus 0 plus 0. So this actually proves that Ix is a homogeneous prime ideal. So notice it's not enough just to say it's a prime ideal and you're done. You actually have to go one step further and prove that it's a homogeneous prime ideal. So again, in this case, everything is 0, so there isn't anything much to worry about. Next, let's ask, is it Zariski closed? And so what we can do is we can try to compute the Zariski closure. So here we'll plug in that Ix is the zero ideal and ask, what are the points that vanish for everything in the zero ideal? Well, because f is the zero polynomial, f of p is always 0 for any p. So this here is the whole thing. So what we just shown is the Zariski closure of x is just x. Right, so there isn't anything to worry about here for the Zariski closure. So we can conclude now that projective N-space is a projective variety. Because again, we proved these two. We proved that Ix is a homogeneous prime ideal, and then we proved that it's equal to its own Zariski closure. Right, so any questions on how we did this here? Okay. All right, let's keep moving. So now let's take a look at the homogeneous coordinate ring. Well, because we're dealing with the zero ideal, then the homogeneous coordinate ring is just S again. So this actually proves that the polynomial ring S is the homogeneous coordinate ring of projective N-space. Right, so that's how S and Pn are related. Finally, what's the dimension here? So we know that the dimension of S is n plus 1. So again, this was a homework assignment. If you have a polynomial ring here in n plus 1 variables, then the dimension of the ring is n plus 1. So that's what we mean by the cruel dimension. So now we can compute the dimension of N-space as the dimension of S minus 1. That's why I said before that minus 1. So that means that the dimension of projective N-space is n. So we just proven that projective N-space is n-dimensional. But of course, this is exactly what we expect to happen, right? We expect this to be a projective variety. We expect it to be n-dimensional. So this just makes sure that all of the definitions are consistent, and we get back what we expect. Okay, any questions on this example here? Okay, so I think in the last few minutes, I'm going to try to do this here. We'll see how far we get. As I mentioned earlier, I want to try to say a little bit behind how this might be related to the prime ideals that we discussed earlier with affine N-space, with affine varieties. So remember that we said that a prime ideal is homogeneous if we can write it this way, but intuitively this means that it's generated by homogeneous polynomials. So I just can't pick any polynomials. I have to be careful to pick homogeneous polynomials. And so this actually means now that this quotient ring is a graded ring as well. Right, so I just want to emphasize that's part of the reason we're doing this, is that now we have another graded ring and everything is nice. So remember that before we talked about this whole thing of a maximal ideal associated to a point. So let's try to do the same thing here. So pick a point, and let's try to associate a maximal ideal to it. Right, so we have this maximal ideal MP, but here's the problem. This is not a homogeneous prime ideal because these polynomials here, xk minus ak, they are not homogeneous polynomials. So we can't really use MP here and just run through all the definitions. So we have to be a little bit careful to modify the definitions to get what we want. So again, here, if we just pick a point, we might think MP here is a maximal ideal, we're done, but this is not a homogeneous maximal ideal because it is generated by polynomials that they are not homogeneous polynomials. So we're gonna do a little trick. Take a look at the following. Let's do AI times xj minus aj minus aj times xi minus ai. So I know now that these here are elements of the maximal ideal, right? I mean, this here, we just get is an element of the maximal ideal. But if I stare at it, this is actually homogeneous of degree 1. Because again, this is AIXJ minus AJXI. So it is homogeneous of degree 1. Now, it could be that I've actually chosen things in a silly way so that everything here is 0. So that's what I mean by this here. So I might have to possibly say that it's the 0 polynomial. It's going to be either one of those two, either be degree 0 or degree 1. But still, I've taken now 2 generators in MP, and I've written down a homogeneous polynomial. So let's make the following definition. Let's consider the ideal generated by these homogeneous polynomials. And if I stare at this the right way, then I see that that is actually this ideal, this nice homogeneous ideal. So again, I've just kind of modified the MPs just a little bit. So now it's generated by these homogeneous polynomials. So now things should be good. We should be able to work out exactly what we want. But first, any questions here on how we modified the definition from just polynomials that we want to now homogeneous polynomials? Okay. All right, so let's try to finish up some things here. So again, remember that we started with our maximal ideals MP, and we modified things a little bit so that now we have this ideal generated by these homogeneous ideals, these homogeneous polynomials. Well, remember that F, that is S0, is not in MP because MP is a maximal ideal. However, I claim that every one of these SEs is in this Proj MP if and only if these here are equal to 0. So here's one way to see that. Say that all of these here are 0. Then this here should just be the 0 ideal. Right, so let's see. So I think I kind of said something here that's not exactly right. Right, but the point is that you actually do run into a weird problem if these here are all going to be 0. Right, so sorry, I have to kind of clean this up in the notes. I didn't say this exactly right, the way I put this here. But let me now kind of finish up saying this. So what we've done is if you give me an equivalence class in projective space, I will associate that to a prime ideal, Proj MP, and it has the property that it does not contain this ideal here. So this S plus has a name, it's what is called the irrelevant ideal. So it's the ideal that's simply generated by x1, x0, ... through xn. Or you can also say that here, it'll just be the direct sum of all of these here, the SEs. Right, but either one of those would be fine. So If you wanted to know why we think of this Proj MP, this prime ideal here is like a maximal ideal, it turns out that you can prove that this here is maximal amongst all homogeneous ideals contained in MP, yet not containing the irrelevant ideal. Right, so I'm not going to worry about saying much about this today. We'll kind of come back and say this later. So in general, if you have a projective variety, then you actually can write down the following abusive notation. So we're going to talk about this more next time, but let me kind of quickly say that what's happening here is this. You start with the projective point. You then write down this prime ideal that I've written here up above, what I'm calling here Proj MP. Right, so this prime ideal. Now, I really want to keep track of the grading, so I'm going to assume that we're only working with homogeneous ideals, so homogeneous prime ideals that do not contain the irrelevant ideal. So again, it looks like the collection of all prime ideals, but I only want those that are homogeneous because I have to keep track of the homogeneous generators. And moreover, I don't want them to have the irrelevant ideal. So we're going to come back and talk about this more next time. I wanted to kind of quickly introduce this today because it does take a while to have all of this sink in for it to make sense. So any questions on what we kind of introduced today? Okay. All right, well, let's maybe call it a day then. So remember that we're going to talk about this in much more detail on Monday. I want to slow down things a little bit and actually discuss several examples in detail to kind of make sense of all of these things here. All right. Okay, well, you all have a good weekend, and I'll see you on Monday then.
Have a good weekend.
Have a good
May I
weekend.
come to your office hour this afternoon?
Yeah, I will be around. That'll be fine.
Thank you.
Okay,
See
you're welcome. Okay, all right, take care, everyone.